Have you ever stopped to wonder how your phone knows if your password is correct? Or how a video game knows in that split second that you've just won? Well, it's not magic, not really. It's logic. And at the very heart of pretty much every piece of software you've ever used is this simple but incredibly powerful ability, the power to make a choice. Today, we're going to pull back that curtain and see exactly how algorithms decide.
So here's our game plan. We're going to start with why making a choice is so fundamental in code. Then we'll get into the three main tools that programmers have in their toolkit: the simple conditional, the more powerful composite conditional, and the super useful case structure for handling lots of options. And finally, we'll see how these simple blocks are stacked together to build some really sophisticated programs.
You see, for an algorithm to be useful, it can't just be a straight line of commands, one after the other. That's just not how the world works. It needs to be able to react, to adapt. And when it gets to a fork in the road, it needs a way to figure out which path to take. I mean, really think about it for a second. When you type your password into an app, the software is doing something. It's asking a very specific question. Does the text you just typed in match the text we have saved? And the answer to that question, a simple yes or no, a true or false, determines everything that happens next. That, right there, is decision-making in action. Now, the technical name for this fork in the road is a conditional structure. All it is a command that checks if a certain condition is true or false. And based on that one simple answer, the algorithm gets pointed down one path or a completely different one. This is the absolute fundamental way that code makes a choice. So let's start with the most basic version of this idea. It's called the simple conditional. Think of it as a one-sided decision, and it is the very first building block we absolutely need to get our heads around. And the logic here is, well, it's beautifully simple. The algorithm is flowing along, and it hits that diamond shape, the decision point. It asks a question. If the condition is true, it follows the path and executes a specific command. But what if it's false? Well, if it's false, the algorithm just skips it. It completely ignores that command and moves on. The simple conditional only does something if the condition is met. Otherwise, nothing happens. Okay, so how do we actually form that condition in the first place? We use these things right here, relational operators. These are basically the symbols that let us compare two different values. We can check if something is equal to, not equal to, greater than, or less than something else. You can think of these operators as the basic vocabulary our algorithm uses to ask its questions. But what if the questions we need to ask are a little more complex? What if a student needs a grade above a certain score and their attendance is over 80%? For that, we use logical operators. The AND operator is strict. It requires all of the conditions to be true for the whole thing to be true. The OR operator, though, is a bit more relaxed. It only needs one of the conditions to be true. This lets us build much, much more specific and powerful questions. All right, let's make this real with a classic problem. We need to build an algorithm that takes two grades, calculates the average, and then decides if a student is approved or reproved. And let's say the passing grade is a 7. So how would you actually build this with the tools we have so far? Well, one way to do it is with two separate simple conditionals. First, the algorithm calculates the average, which we're calling M. Then it asks the first question, is M greater than or equal to 7? If that's true, it prints approved. Okay, great. Then it moves on and asks a second question, is M less than 7? And if that's true, it prints reproved. Now this works, but notice something. It always has to ask two questions no matter what. And that little inefficiency, that tiny bit of wasted effort, brings us to a much more elegant way to handle these kinds of choices, the composite conditional. This is where our algorithm starts to get a lot smarter. So, unlike the simple version, the composite conditional explicitly defines what to do for both outcomes. If the condition is true, it executes command 1. But if it's false, it executes command 2. There's no longer a path that just does nothing. Every single outcome has a clear, predefined instruction. This is the classic if-then-else structure that you've probably heard about. Now, let's go back to our student grade problem, but this time, let's look at it through the lens of efficiency. On the left, we have our original solution with two questions. On the right, we have the new if-else structure. And here's the crucial difference. The version on the right only asks the question once. If the average is 7 or higher, it prints approved, and it's done. It completely skips the other part. And if the condition is false, the algorithm doesn't need to ask another question. It already knows the only other possibility is that the student is reproved. So it immediately runs that else block. It's just so much more efficient. Okay, so understanding exactly how these structures work, especially how that else statement latches onto an if, is absolutely critical. So here's a little challenge for you. Take a look at this algorithm. Can you spot the flaw? So this piece of code is supposed to take two numbers and tell you which one is bigger, or if they happen to be equal. It uses two if statements. The first one checks if num1 is greater than num2. The second one checks if num1 is less than num2. And, importantly, it has an else attached to it. So, what do you think happens if we give it the numbers 7 and 5? This is the output you'd get, which is clearly wrong. And this perfectly illustrates the problem. The first if statement correctly sees that 7 greater than 5 is true, and it prints the number 7 as the greater. But the algorithm doesn't stop there. It continues to the second if and asks, is 7 less than 5? Well, that's false, and because it's false, it immediately executes the else part of that second statement, which prints numbers equal. That else only belongs to the if that comes right before it, and that creates this really subtle but critical bug in the logic. So we've seen how to handle one choice and how to handle a choice between two different paths. But what happens when you have a whole bunch of different specific options? Think of a menu at a restaurant or an ATM. For that, we have another fantastic tool, the case structure. A case structure works kind of like an old-school telephone switchboard. It takes a single variable and it checks its value against a list of predefined cases. If the variable's value matches value 1, great, it runs the code for that case and it's done. If it matches value 2, it runs that code instead, and so on. It is a much cleaner, much more readable way to handle a situation where you need to choose one action from a list of many possibilities instead of writing a super long and messy chain of if-else statements. All right, we've covered the three core types of conditional structures. So now let's pull it all together and see how these simple rules become the actual foundation for really complex software. So, just to recap, these are our essential tools for making decisions in code. We have the simple conditional for when you only care about the true case. We have the composite conditional, our classic if-else, for when you have a clear choice between two distinct paths. And we have the case structure for picking just one option out of many. But the real power, the magic, comes from combining them. You can nest one of these structures right inside of another. For instance, think about classifying a triangle. You'd first ask, are all three sides equal? If that's true, you're done. It's an equilateral triangle. But if it's false, you go into the else block. And inside there, you ask a second question. Are all three sides different? If that's true, it's scalene. And if that is also false, well, then by elimination, you know it has to be isosceles. See that? By nesting these simple questions, we can navigate some really complex logic. From something as simple as checking a password to something as complex as diagnosing a medical condition based on symptoms, it all just boils down to these fundamental structures. These simple rules of logic, if then else, are the tiny building blocks that allow software to reason, to react, and to make the billions of decisions that power our entire digital world. So the real question is, what will you teach it to decide next?